All right, we'll get started. This is talk about the Go language. Hopefully you're in the right spot. I'm Brad Fitzpatrick. I work at Google on Go. I've been working on Go for about 5 years now. At Google for a little bit more than that. I previously worked on Android for a little bit, so I have a little bit of Java street cred, but I don't write much Java these days. I used to write in lots of languages, and now I pretty much only write in Go. I have a lot of slides to go over, so I'll be going kind of quickly. Hopefully I speak understandably. I want to talk about what is Go and kind of like why it exists and maybe how it's different, why I personally love it and why I first started getting addicted to it and why I joined the Go team. Then I assume most people here know Java, so I'll do a little comparison between Go and Java and go over some examples of Go and why why the concurrency features of Go are really fun. We'll build a little like demo app and go over some of Go's tooling and then kind of talk about the history of previous Go releases and what's coming up for the upcoming Go 1.5 release. The website golang.org says that Go is an open source programming language that makes it easy to build simple, reliable, and efficient software. One of the key words there is simple. Go is actually a very, very small language. You could probably learn it in a weekend or a week and get very comfortable with it. It'll take you maybe 3 months or so for your mind to kind of like warp around the different style of writing code. It's kind of hard for me to write in other languages now because I want to approach them the kind of like the Go way of doing it. But it's a really great language for lots of things. The design of it started in about 2007 from Robert Griesemer, Rob Pike, and Ken Thompson. Ken Thompson, you know, of course, from like C and UTF-8, and Rob Pike's worked on lots of languages at Bell Labs and stuff. Robert Griesemer worked on V8 and the Hotspot JVM stuff. And then Ian Lance-Taylor works on like GCC and Gold, the linker, and Russ Cox, who's just like a hacking machine. They joined the project early on, and Ian Lance-Taylor was working on the GCC compiler for Go, and Russ Cox was working on the other compiler, Go. Basically, everyone works on everything. It was open sourced in 2009, and there's been tons of contributors. We do all of our development in the open. We pull it into Google like every 6 months, but all the development in the public mailing list and the bug tracker and this stuff it's all an open source project. The language has been stable as of the Go 1 release in 2012, so that's when we made a compatibility promise and said if your code works in early 2012 when Go 1 came out, it'll still work today. So we can add little things, but basically it's frozen, so it's a pretty stable language at this point. Go came about because we were kind of wasting lots of efficiency at Google writing in C++ or Python. Sometimes, people choose Python or something because it's fun, but it's really bad for the computer, or they choose C++ and it's kind of just a pain in the ass for the human, but it's good for the computers, and Google has lots of computers, so it'd be nice if we had something that was efficient for computers and easy to like interact with lots of systems. Google has lots of computers, and typically when we run a job, a collection of containers or whatever, there'll be thousands of them, and so a lot of them are talking to each other, and there's just lots of stuff going on. So it would be nice to have a language where concurrency was kind of a built-in concept, where it was easy to keep track of user requests and talking to your peers and figuring out things failing. And so yeah, Go is basically designed for big systems, but it's also designed for big projects or big teams. These are intentionally old numbers because I guess Google doesn't really let us publish current numbers, but in 2001 we had like over 5,000 developers and 40 offices. There were 20 changes per minute going into our revision control system. 50% of the code base was changing every month, and just tests and tests and tests. The tests are just always running. We have a whole like almost data center just dedicated to like running tests. We have one giant code tree. So we basically have one repo, and the self-driving car and Gmail and it's in the same repo. And things can depend on each other. There's visibility rules, so you can not have spaghetti dependencies. But our build system and test system knows that if we check something in here and it affects that thing over there, it'll run the unit tests for it. So making sure the build system is fast and efficient for running all these tests really means we have to have like a smart compiler and proper module system. So, and we also have you have to assume that the person who is debugging your code is not the one that wrote the code. You may quit the company or change projects or whatever. So we care really more about code readability than code writability half the time, and it has to be easy to refactor things and do mechanical transformations on code. So a lot of decisions in Go are specifically around making it work with big teams, or you've often heard the term programming in the large. So we use it, of course. One of the most prominent products is I guess we call it the data compression proxy. If you go into Chrome on your phone and say compress data, means all your unencrypted stuff gets sent over a compressed, speedy connection to Google, and then we optimize the images and CSS and compress things down. That's all written in Go. There's also things like the download server. I rewrote that from C++ to Go. Got a bunch smaller and faster. All of YouTube's MySQL traffic goes through a Go proxy that does MySQL sharding and load balancing and crazy stuff. So Go is a really easy language for writing crazy servers with lots of connections and lots of fan out and stuff, but it also runs on Android and iOS and stuff now. So it's a general purpose programming language you can use for just about whatever you want, but it was originally written for servers. Other people use it too, but people put it on buses. This was at a conference last year. But yeah, it used to, people have heard of Docker is written in Go, but nowadays lots of people use it. So why I love Go personally, when I pick a project, when I start a new project and I have to pick a language for it, I've always considered it as lots of trade-offs. So I'm going to make some crazy claims here and try to offend some people, but I'm just doing it for fun. This is my disclaimer out of the way. I gave this talk a while back, and it was, have you seen the movie Anchorman? There's a line in there where this guy says, 60% of the time, it works every time. And they replied, that makes no sense. So I was explaining to someone that Go is kind of 90% perfect 100% of the time. So when you start a new project and you're deciding, do I want this to be good for humans or good for computers, you can just say, screw it, I'm just going to use Go and it'll work fine. So before Go came about, I was an early Perl guy, so I wrote lots and lots of Perl. And when I started a new project, I would basically think, am I going to write this in Perl or am I going to write it in C? Do I care about having fun and being productive, or do I care about writing something efficiently? Sometimes I would write in Java. But the good stuff about Perl was, it's fun and expressive and you get shit done. The bad part, and then there's just all the other scripting languages, which as far as I'm concerned, they're basically the same as Perl. They have the same properties. But if I wrote in Perl, it wasn't really fast. And if I had to do something fast, I would have to write in this glue language called XS that let me call from Perl to C and C to Perl. And I could only do one thing at a time because it's kind of single-threaded. And if I wanted to deal with event-based programming and write a server, I'd have all this callback hell. So it's a trade-off. Python, Ruby, JavaScript, kind of the same properties. They're kind of slow and can do one thing at a time. So your decision was, do I choose Perly Python Ruby script and something that was fun for good for the human, but really bad for the computer? Or do I write something like C or C++ where you're closer to the machine and you could write something fast, but it's not that fun? And then Java is kind of in the middle. It has some other kind of annoying properties like slow startup. And then there's bizarre choices, I guess you can write it in PHP. So I like to visualize this kind of like this. That there's good for the humans up here, which is, people love comparing Ruby versus Python versus JavaScript. What's their favorite language? No one likes Perl anymore. But people pick those, but they're all basically the same. They're all slow, and they can do one thing at a time. And then there's the fun language, or the fast languages for computers, in C++. And Java's kind of in the middle here, where it's kind of fun, but kind of tedious, and it's kind of fast, but not quite as fast. So really what you're looking for is some language up in here in the happy spot, right? That's really good for computers and really good for humans. But that's a magical unicorn. So you think, oh, maybe I'll make this project and do a mix of languages. I'll do the fun parts in a scripting language, and I'll do the important parts in C. But then you're left you're stuck with this position where you're having to call back and forth, and you have to decide, where am I going to call back and forth? And the problem is this changing between calling conventions is always really expensive, because you can different calling conventions, so you have to copy the arguments back and forth, and so you don't want to do it. So you kind of just be lazy and you stick in one language, or you're like Google and you write everything in C++ when there's no purpose to write it in C++. And so then the other thing is you're writing a server and you have to choose kind of an event model. Do you want to deal with threads, or do you want to deal with events? If you're in a language that actually has threads, whether it's like C or C++ or Java, you can, but they're really heavy. They have gigantic stacks. Typically, they'll take up megabytes of memory, or you make the stacks too small and you stack overflow and crash. And a lot of times you're stuck with these decisions, like you're in Java and you're making a new thread pool. And how many threads do you use? And you just kind of pick out a number. You're like 8, 16, I don't know. Or you're in a scripting language, and basically your only choice is events, because your scripting language maybe pretends to have threads, but they don't really work, or they're really, really slow. So you end up using some event machine or Node.js or callback, 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 and you have futures and promises, but you can't really read your code. It's all either super indented or it's jumping all over the place. Or now languages are starting to add weight async stuff, so you just sprinkle that all over your code. But it's kind of disgusting. So on another one of these little graphs, you have languages that are good and fast at doing concurrency, and then you have languages where the code is actually readable and reads from the top down. Except for no one really likes Erlang because they think it has a bizarre syntax. So your choices are code that's disgusting and slow, or code that's disgusting and fast, but it's no great answers there. You kind of want something that's fast and readable. So I decided it sucks. Everything is terrible. But then I found Go, and I kind of found that it was a great language because it lets you write high-level code when you want to write high-level code, and when you want to write low-level code, Go lets you just choose to write low-level code in that little part. So you just start high, and if you profile it later and you find something that's slow, you write that little part in thinking about how the machine works, or thinking about your allocations or whatever. Go has really good profiling tools built in, so yeah, I just write things in Go now. And I found that instead of this, I have something more like Go is, maybe not quite as fast as a scripting language, or not as fun as a scripting language is. And it's, a little bit faster than Java, catching up with C++ and stuff. But it's the closest up to the utopia, happy unicorn zone up in the top right there. And in terms of concurrency, because Go has really good, I'll talk about Go's concurrency story later, but Go lets you write top-down code, and it's really fast. So in the meantime, Clojure and stuff has kind of copied a lot of concepts from Go, and C# got its async and await noise. So I don't know. All the other languages still kind of suck, and you're bouncing all over the place, or it's really expensive and uses lots of memory for stacks. But Go is really efficient concurrency. So this is a fun graph. Internally at Google, we have a little service that analyzes all your code and kind of gives you stats about what languages you write in. And I guess you can't really see, but this is 4 or 5 different colors here. There's a blue and a purple and a green, which is it's like C++ and Java and Python. And I used to write in a mix of languages. And then Go came about, and I pretty much stopped writing in every other languages, and I pretty much only write in Go now. So I don't even write shell scripts or little bash things in bash. I just will write up a little Go program instead. So it's a really fun language, really efficient. So we'll actually look at some code in a bit here, but comparing Go and Java, a lot of it will be familiar. The syntax is kind of similar. It has curly braces. You can indent things, but it's not like Python where white space matters. It's garbage collected, so it's a memory safe. You can have null pointers, so you get those same sorts of crashes. His runtime bounds checks, just like Java. Variables are always initialized to either whatever the normal 0 value is, whether that's a null pointer, which we call nil, or 0, 0.0, empty string, whatever. We have methods. So you can make a type. We don't have, well, I'll show you some things we don't have. We have interfaces. We have type assertions, which is like Java's instance of. And we have reflection. But unlike Java, there's no JVM. We don't run on the JVM. We get a static binary, and we can cross-compile to like any operating system and processor architecture. So if you're on a Mac and you want to produce an OpenBSD ARM binary, you just set an environment variable and you get that binary. Likewise, Mac to Linux, you just copy this one Linux binary to your server and run it. And so Go lets you control memory layout. So if you have like a struct or some record type and you put another one inside of it, internally it's not like a pointer to this memory over here like it is in Java. So you can actually like line things up in memory really compactly, which is nice for your processor, for your cache. Go has actual closures, none of that final stuff like in Java, where if you have an inner class and you want to refer to something outside of it, you have to make it final. You can actually just read and write whatever you want. We have built-in maps and slices that are generics, but only for maps and slices, and we have concurrency built into the language. But we have lots of stuff that is omitted. So there are no classes. You can make a type in Go, and you could put methods on that type, but there's like no inheritance, there's no constructors. We just have constructors by convention. You make a function, and it's called new whatever, and you return something. But in general, we kind of encourage you to use what we call the zero value. So if you make a type called foo, we kind of say for most cases, an uninitialized foo should be usable right off the bat. So in the standard library, we have a package called bytes, and it has a type called buffer. So in your code, you refer to bytes.buffer. And without any initializing, without any constructor, that thing just works, and it's a byte buffer. And it'll lazily initialize its state as needed the first time it's used. So that sort of style of really simple is popular. There's no final. There's kind of like no. The string type is immutable, but a lot of types are just you don't mess with them by convention, and there's different styles. But we don't have exceptions. We don't have annotations, and there are no generics, which you've probably heard people complain about this one a lot. It does sometimes suck that we don't have generics, but it doesn't come up that often because the language has maps that are built in that are type safe and has slices and channels that are type safe. So occasionally you need to fall back to writing some container type, and you use the empty interface, which is like a Java lang object basically. It can hold anything, but not that efficiently. And so you lose some type safety occasionally. It does mean we can't put, our standard library doesn't have a lot of like type safe algorithms and stuff. There are various proposals to add generics to Go. A lot of them are not that great. There's a document that kind of summarizes all the different approaches we might take. It'll probably happen at some point, but there's no real priority to do it. So there was this talk by Simon Peta-Jones where the title was called Haskell is Useless. And he was kind of talking about there's languages that like let you get stuff done but don't really have an interesting type system. This is kind of like all these languages that, no real type system. And then there's languages with beautiful academic type systems, but people find really hard to use and you can't really get anything done. Go is basically here. If you think of Go as just like a faster, more efficient, like easier to write C, like an upgraded C, it's fine. But Go doesn't really pretend to have an amazing type system. It's a very small type system that's easy to compose and use, but it's not like a Haskell or anything, or a Scala. So Go very intentionally leaves a lot of this stuff out because it's trying to be a really simple code. Like I said, for big engineering teams, it's really important that you can read other people's code. So a lot of times we prefer that you write a 3 or 4 line loop rather than having some like magic package that has some function that does it all for you. So yeah. So the code is easier to read, and we encourage you to not be that clever. Sometime in our documentation, we say like in the documentation for the mutex and the sync package, and where we document the memory model, we say if you're reading this document, you're probably doing it wrong. Like you're doing something too clever if you have to come read this document about the memory model. Anyway, so let's look at some Go. Make it a little bigger. So here's about the equivalent of the Java. The program starts in a package called main and a function called main, and when the main terminates, the program's over. So here's a little thing where we can run the program, and we could say hello devox and run that. Here's hello world web server, because everything needs the web server. It's in the standard library. You can make your own router, your own MUX if you want, but the standard library has a simple one built in. So here we're saying, here's HTTP, the package name, and we're registering a function at an endpoint. So at the /hello handler, we'll run this function, and this function handle hello takes a response writer. This is how we write the HTTP response back to the connection, and here's the incoming request. This is a pointer to a struct type here. So if we run this, it starts up, and it's running here. And you can see down here, I have a little web server running in my slides. I'll kill that. So some things that are going on here. Go doesn't use the words public or private or protected. We basically only have two visibility states. There's public and there's private. We call it exported or unexported. And if it's public, it's capitalized. And if it's lowercase, it's not. So in this case, HTTP is the package name from NetHTTP up here. And handlefunc is a public function that's in that package. And also listen and serve is a public function that's in that package. So this is a little convenience thing to quickly run a web server. It listens on that port. And if the listen fails, perhaps you're trying to listen on port 80 and you don't have permission for port 80, it'll return an error. And so basically this blocks and runs forever. And what happens is whenever a new request comes in, it starts a new Go routine, which is like a lightweight thread. We'll talk about more in a bit. And that runs separately and runs this function. Nil here is basically what a handler to use. And if that's nil, the default is to use the router that's built into the HTTP package, which we registered here. So we're going to build this. We're going to kind of build a fake Google search front end and back end. So the thing we're going to build will look like this. It'll have a search handler, and it'll take one parameter Q, which is the search query we want to give, and it'll give a little page like that. So here is the thing we'll run. Sitting on 8080. I still have that thing up. Nope. And it says missing Q parameter, and we could add a Q parameter and say like devox, and that's the results. Or we could say, devox PL, and we get those results. So that's actually coming from Google. So we'll talk about, I'm going to close that. So just like before, instead of registering something at / or at, I guess this one registered it at hello, we'll register a search handler, and yeah, just like before. Now we'll have a handle search function. In the handle search function, we'll look at one of the form values, get the Q parameter. This colon equals here is a short, it's basically short for this, var string equals whatever. The types come afterwards. You can omit them, and then it's inferred from the right-hand side, so it's equivalent to that. But the really short way to say it is just that. Query equals form value of Q, and we say, is it empty? If so, return an error back to that response writer and tell them they're missing a parameter. Send a 400. Some things to note here. This form value is a method. It's a method on the request. So in the HTTP package, there's a type request. So this is a named type, and the implementation of the type, or the concrete thing in memory behind it, is a struct, and it has some fields like the URL and the path, the method for the request. And then this is the syntax for declaring a method called form name on the type pointer to request. And this is the receiver name. In Java, this is always called this. But in Go, it's just another parameter. And you can actually call methods on a nil pointer. Actually, show that we have this playground at play.golang.org. I can actually make some type here that's a struct, and I don't know, maybe I'll have some field name. And I could make some function that's on a pointer to t called, foo. And maybe I'll make that say, I'll say hello. So I can make here a pointer to t. I'll make this very explicit that it's nil, but it would be nil anyway. and I can say t.foo, and that compiles. That compiles just fine and says hello. So you're totally allowed to call a method on something that's nil because it knows statically that the type of t is a pointer to t. And so this is just another parameter. And if I were to actually print the value of that, you could see that it's 0. But once I tried to access it, and I said like t.name, that's where I would blow up. So it would do the first line fine, but this is a 0, so you can't actually look inside that memory. So we have a pointer or a method called formValue on a request, and it takes a key. It's a string. The types come after it, unlike Java. That makes sense for various reasons, because a lot of times you can omit them, and it returns a string. So we have the Q parameter. The next step is we're going to actually fetch the results from Google for this little front end. In this case, we're going to look at the current time. So this returns a value of type time.time. And then we're going to do a search and see how long that took. So this returns a time duration, basically the number of nanoseconds since this happened. And if there was an error, maybe like there was no network or something, we'll return a 500 back to the client. So the search function, the one that we're calling right here, takes a query, and it's going to return a list of results or a slice of results. So that's basically, we have a difference between arrays, which have a fixed size, and a slice, which is like a variable-sized window onto an array. And so it'll return two things. It'll return a slice of results, so 0 or more, and it'll return an error. And by convention in Go, if some function returns an error and the error is not nil, basically, unless you document it otherwise, the assumption in Go is that the first parameter is useless. Error is a built-in type in the language. Basically, the minimum thing that it has to have is some method that describes itself. So it has a method called error that returns a string that just says what it is. But anything can implement the error interface. So if you wanted to have a structured, rich error with lots of information, you can. So once we have the results, we're going to dump them out. Go has a built-in template package in the standard library that we'll use here. And so here, inside the body of the function, you can make types. So you can make a type that's local to just a function. And this is a struct that's a list of the list of results that we got and also how long it took. And then we're going to execute the template, writing to the response writer that we had on the previous, this one, the response writer. And we'll instantiate a value of the type of template data right here and pass that to the template execute function. And it'll dump it out. So the interesting thing here is the template package takes anything that is an I/O writer, and it happens that the HTTP response writer is like a superset of this interface. So any response writer also implements the I/O writer interface. And in Go, interfaces are implicit. You never have to say implements foo. If you have the method and has the right signature, it just automatically works. So here's an example of the little template language. So that's not that interesting. It's like any template language. Here is a little implementation of that search function. So we're going to call this Ajax search API that gets Google Web results over returns a JSON response. So we'll set the Q parameter to add to this, to whatever query was passed in. That'll then encode it, which will do all the proper escaping, and then we'll fetch it. And just like the convention I was saying, where if it returns an error, that means the rest of it is invalid. Here, if the HTTP GET fails for whatever reason, we're just going to return directly with no results. This thing is kind of fun. Defer prepares to call a function but doesn't call it. So it'll evaluate all the arguments to it and stash them away on a stack. And when this function finally returns, however it returns, you might have like 3 or 4 return statements later, the stack is unwound and all these functions are called. So it's kind of a way to clean up after yourself later. Think of it like in Java as like a finally, but instead of having it all indented, it's just like it's a finally on a stack to do later. And so this is how we're going to close the HTTP connection. So maybe this TCP connection will be reused with HTTP keep alives, and we'll be able to like do another request on the same connection. So here we get it, and we have the response. The response body is an IO reader, just like this thing back here was an IO writer. There's another signature in the IO package that defines an interface, something that's readable. And in this case, it's a reader and a closer. So we close it when we're done. And the next thing we do after we have a valid connection, or a valid request from the server, the response from the server, we're going to decode that JSON. And so new decoder takes anything that's a reader, and the thing we get back from Google from the HTTP package is a reader, and we call decode into the address of this variable we have here. And notice that this variable, the JSON response, doesn't have a named type. We just had a little anonymous type here for exactly the structure of the JSON type we want. And we say it's kind of a field called response data in the JSON, and that's going to be an object with something called result, which will be a JSON array with an object called with title, no formatting, and URL. So you can totally make these little types that have, or variables that have a custom type that never has a name. And then this JSON decoder uses reflection to automatically populate the JSON response into this variable. So once we have that, the JSON response, we have a uninitialized slice, so that's just 0 length by default, and we can enumerate over the response data and all the results in there and convert it and append them onto this slice here in the format that we want for our. So yeah, so for everyone, we're just basically renaming this title no formatting as it is in the JSON to title and the URL to URL and return them. So all that was done with just the standard library. JSON is in the standard library, and the templating, HTTP requests and servers in the standard library, URL parsing. So the cool thing about this was you could actually put this on the internet and probably serve hundreds of thousands of requests even a second or per at once. And you don't have to really worry about threads or all this stuff. All of it is handled automatically. Every HTTP request was run in its own Go routine. So we'll talk about Go routines. There was some computer science in the late 70s. And there's a paper about communicating sequential processes. And the basic idea is that instead of thinking about you should be able to have lots of concurrently executing things, and you should think of your code of what it's trying to do and how it communicates with other things, and not really. Anyway, gist of it, you have really lightweight threads, and they talk to each other over channels, and we can pass around channels and stuff. So other people call them fibers and stuff like that. Anyway, so Go has 3 primitives built in that make this really easy. Go routine, which you can think of it as a really, really lightweight thread that's managed by the Go runtime. Channels, which lets you communicate between different Go routines. And the select statement lets you wait on different sorts of communication. The way you launch a Go routine is you just put Go in front of any function call. And then that function basically runs in its own thread you can think of. So you don't really have to think about thread pool sizes or anything. If you want to do this inside of a function, it's totally fine. These are so cheap to create and destroy that you can just use them without thinking about it. You don't have to think about how many operating system threads you have or anything. If a Go routine doesn't have something to do, then the runtime will make sure that it's just in the runtime scheduler. So it'll either use epoll or completion ports on Windows or ktrace or whatever, not ktrace, but the FreeBSD or Darwin equivalents. And so it could either be blocked, it could be blocked in a system call, in which case it actually has a thread waiting for the kernel to reply. It can actually be computing something and running actual machine code, and then it has a thread. But otherwise, if it's just waiting for the network, it'll be using epoll or whatever. If it's waiting for a mutex or a channel send, it'll just be in Go scheduler. And so all of your CPUs that are on the machine will be used by Go routines if they can, and if there's nothing to do, it just takes it'll take 2K of stack. So, yeah, I said every Go routine has by default 2K of stack, and if you run out of stack space, it's just enlarged. And if it uses too much, or it shrinks back down, the stack is shrunk again. So yeah, you could have hundreds of thousands of these, and they're just memory. Channels you make with the make function, which is built into the language, and they have a type. So this C channel is used for sending strings between Go routines. So one Go routine could be doing the send operation here, sending to the channel, and this one is receiving from the channel and assigning to the variable S. And there's two types of channels. There's buffered channels and unbuffered channels. This one is unbuffered, which means this send here blocks and waits for somebody else to receive it. So you can use it as a synchronization point as well. So this will not proceed down to here until this has actually been received.
What about interruptions and timeouts, things like that?
The question is, what about interruptions or timeouts? There are no interruptions and timeouts. That will actually block forever until it happens. This is great. In Go, if you want to sleep, you say time.sleep 1 second, and it will sleep 1 second. You don't have to like wait for interrupted exception and all that sort of crap. So select you can use if you want to do a timeout. You can wait for one or zero or more things to happen. And you could say, so each one in a select, it's like a switch, but it's used for communication cases. You could put a receive in here, or you could put a send in here, and exactly one of these will happen. And if you want, you can put a default case. And so if none of those are available, it goes to the default case. So that's how you can test if something's ready, or you can, one thing you could do if you were wanting to wait for something, but well, I'll show you a timeout case coming up. So we wrote the front end for the Google search. So let's write kind of a fake fun back end for the Google search. So if you go to like google.com and you search for something, you notice there's like, there's ads, of course, and there's results, and there's like video search and image search and map search and all that stuff. So the way that's actually implemented is things come into Google and they're like fanned out to lots of microservices, I guess you will call them, and each microservice will like return a certain type of search results. So we're going to make something that kind of fakes this out. We'll make a dummy Google search server. So we're going to make a type called search, which is kind of a type of search to do. And it'll be, the type of the search will be a function that takes a query and returns some result. And then we'll make some fake web search backends. We'll make a web search backend, an image search backend, and a video search backend. And each one of those is initialized by this function called fake search that takes a kind and returns a search, which is this closure here of that takes a query, and it sleeps some random amount of time between 0 and 100 milliseconds. And then after 0 or 100 milliseconds, it's going to return the whatever result for whatever. So for this type. So it'll say like if we, it'll return image result for, Devox PL or whatever we search for. And here's our package main, func main. We're going to look at the time, and then we're going to Google for Golang, or we could, Google for Devox, and then see how long the thing took and print it. So if we look at that, we could see that we got a web result, image result, and video result. And it took 150 milliseconds, took 169, 145, 206. And so our initial dumb implementation of that Google function here is just this. We first call the web search one. That web was this variable here for this is our web backend, this is our image backend, and our video backend. So the dumb implementation of the Google search, where we just do it in serial, is we append the web answer, then we append the image answer and the video answer. The problem is each one of these could take 1 to 100 milliseconds, and so overall it could take between 0 and 300 milliseconds. And sure enough, if we run this a few times, 136 milliseconds, 183, 202, just way too slow. No user will wait for that. So the thing to note is there's no reason that the image one depends on the web one, or the video one depends on the image one. There's no reason to do them in serial. So here's a little version in Go that does them all in parallel, does them all concurrently. So what we're going to do is first make a channel of the results within this function, and then we're going to kickoff, we have a little function literal here, a little closure, that closes over the query variable that was passed in, and does the web search, does the image search, and the video search, and when it has its answer, so first it evaluates this, and once it has the answer, it will send it, that's the send operator there, to the channel, and then in the other Go routine, the Go routine that originally got this function called, it will sit there and receive 3 times from whatever channel that arrived in any order. So now if we look at this, took 79 milliseconds, 84, 75, 84. So now nothing should ever be above 100 because each one of these things by itself can only take 100 milliseconds. So we're already a lot faster. Before it could take 300 milliseconds, now it can only take 100. The question is each channel waiting for the?
Because here you're launching 3 routines and they should be parallel, but should we wait for the finish?
Oh, so the question is, should we wait for them? Well, what's happening here is we're running this loop 3 times, and so there's 3 sends that are happening, and there's 3 receives that are happening.
Actually, calling the query in the output, it means we are waiting for result.
Yeah, so so this will block. It'll block the main Go routine or the Go routine, whoever called the Google function, and it'll block that Go routine until one of these in any order. So you notice here the order. So in this case, web was first, then image, then video. But if I run this a few times, now video was the fastest one, and then image, then web. Now web, So they're basically a random order depending on which Go routine was the first one to send. Well, append never fails. So in this case, there's no error. In reality, the results would probably be something that contained both a result or an error or something like that.
Yeah, but you have iterated. So is the problem if one result was not responded?
Yeah, so we'll make this more complicated in a second here. Okay. But servers are slow, or like you were saying, fail. So we want to say that the user is impatient and doesn't want to wait for more than 80 milliseconds. So what we're going to do is we're still going to make this channel, and we're still going to kick off all of these, but we're also going to use this thing time.after, which returns a channel, and that channel is readable after 80 milliseconds. And then we're still going to loop over all 3 result types, web, image, video, in whatever order, and we're going to try to receive from a channel. But if the timeout one is readable because it's been 80 milliseconds, we're just going to return from the function and give up. So in this case, we got them all in under 80 milliseconds. It was only 9 milliseconds there. Oh, but here, 2 of them timed out, so we only got the image result. And okay, we got them all. Oh, the video result timed out, so we only got image and web. And you can imagine that instead of a timeout, this was because one of them had an error or something, or had a bad disk, or the machine was down. One thing to note here is that because this is a blocking operation, that Go routine will never die if it never gets to the end, and if no one receives from this channel, you basically have a leaked Go routine that's there. So what we do here is we made a buffered channel. So this channel has space for 3 results, and it means the sender will be able to send and put it in the buffer before somebody goes and receives it. So that way, if 80 milliseconds elapses, and this one was really slow and this one was really slow, when they do finally get around to running in maybe a second or 2 seconds, there's space for it, and they don't have to care that this function has already returned and nobody will ever read from that channel. In reality, you would probably pass a cancellation context to each of those things. So when this function returned, you would cancel their subcontext and make them go away and stop wasting resources. But this is a simplified example. So we have these backends that are dead or returning errors or just being too slow. So we can throw money at the problem and just have more replicas. So here we're going to write a function called first, which has a query type and has a number of replicas. ... here means is a variadic list, so 0 or more things of that type. And then what we're going to do is we have this little function here, which is a closure that takes an index, takes some integer index, and sends to the channel, the one we just made here, and queries that replica, which is one of these functions, with the query that we got passed in. And then what we're going to do is we're going to go over all the replicas. Range, basically this returns the index of one of these things. So we're going to say search replica 0, search replica 1, search replica 2. And then instead of returning, so we launched like 3 of these, and each one of them is doing a send, but then we're just going to return, we're going to do one receive. So whichever one of the replicas returned first, we'll use its result. So now, instead of just doing the search, we could have this backend here we call replica 1, and this one called replica 2. And when we run this, replica 2, 1, and now replica 1, 1. And so if you run this a few times, it's faster than 100 milliseconds usually. So that we can combine this all together. And we could have, let's say we have 2 different servers doing the web backend, web 1 and web 2. We have image 1 and image 2, video 1 and video 2. And when a Google search result comes in and we want to query the all of web, image, and video, really what we're doing is we're querying the first of 2 web backends, the first of 2 image ones. And now our tail latency, it will be much better. Now we're only getting 64 milliseconds, 42, 77, instead of up to 300. And we can tolerate different machines dying and stuff. So here 2 was fastest, video 2 was fastest, web 1 was fastest. And we have no locks in there. There were no mutexes or no condition variables or no callbacks. You just write straight down code. So we went from something that was serial and was taking like 300 milliseconds and just going down to something that was failure sensitive and was fast and concurrent and robust and replicated. And so I really like being able to write code like this and write code that goes down, splits in 2, and then joins back. And yeah, it's really good for servers. In terms of Go's tooling, we have one standard formatting style. I know people like to debate where semicolons go, or indentation, use tabs or spaces or all this sort of crap. We have a tool called GoFumped that basically ends this debate. We have kind of one standard style. If I were to put all this code kind of here, and I don't know, it basically doesn't matter. If my code is like that and I hit format, it comes up in the standard style. And everyone in the community uses this. Something like 99% of the code in the open source is all Go formatted. We also have a tool called Go Imports that automatically writes your imports for you, so you don't have to. You just write your code. And if you had some code here, and you said, fumped.println, hello. If you ran this, you would get errors saying that there is no internet. Yeah, undefined fumped, which is how we pronounce FMT. But if I check this little box here, it'll add the imports in. And if I delete this and run to get format again, the import goes away. So most people have this in their editor on their onSave hook. And then they never have to really think about what imports they have to use. We have this Go tool that lets us compile things. So we can say go run x.go, and that just quickly runs it. Or you can say go build to compile it first, and then you have a little binary. We can say go test to run our tests, but we have no test files here. But we can write a little test. Test foo. Takes testing.t and says, save that. Now we can run go test and run our unit tests. So the Go tool does lots of stuff. You can say go get and say go get rc.io bench stat. And that will fetch it from the internet and into the right place in your workspace. and compile it. Now I have a bench stat program. So yeah, the Go tool does lots of stuff, has really good tooling. We also have a lot of like refactoring tools. EG is like a refaster for Java that does example-based rewriting. This Oracle answers questions about your code. You could say at this point in the file, where was this defined? Where was a channel send or channel receive from this coming from? Who implements this interface? Go rename does global renaming of identifiers or types or whatever. That is totally safe, or it'll tell you that it's not safe because if it introduces an ambiguity or a conflict. And we have IDE and editor support that all these things plug into. Oh yeah, so I showed you that. Go imports will automatically write your import lines. The tooling does go get and stuff. Godoc.org is kind of just a summary index page of all the code that's out on GitHub or wherever. And you could search for things like if you want to control the GPIO pins on your Raspberry Pi, or if you want to, I don't know, have a VNC server, or I don't know, deal with ping files, and then you can go like look at the docs for things. So, yeah. So then there's all these tools, but these tools basically plug into your editor. So it doesn't matter if you use Sublime or IntelliJ or Emacs or Vim or Eclipse or whatever. All these tools we write to be really generic, and then when we do want to integrate them with an editor, the person who uses that editor has to do a very minimal amount of work. So if you want to like rename the identifier that's under your cursor, the editor just has to say, I'm on this position within the file or this line number or column, and then we'll do the rest. And then the editor just has to do a reload. So we don't really have an official IDE. We kind of just bring the tools to you, and your editor should plug into them. So in terms of roadmap, we had a lot of old releases, but the major releases come about every 6 months. Go 1 was in 2002 or 2012, at the beginning of the year, and this was the release that had the compatibility promise that said, we won't break your code. If your code worked then, it'll continue to work. The next release, Go 1.1, took a year, and we decided a year was too long to do releases, and this is when we switched to the 6-month cycle. That release basically just got faster, and we had a race detector. Go does let you have data races, so you could have multiple Go routines mutating memory. That's kind of a bad thing to do, but the language lets you do it. In general, you would use Go routines and channels instead and avoid these sorts of bugs. Go 1.2 had a preemptible scheduler for Go routines. So if you had one Go routine just spinning there, it wouldn't slow down anything or like cause other Go routines not to run. Go 1.3 had copying stacks. So what we used to do is we would have a little like 4K stack segment, and when you ran out of stack space, it would allocate a new stack, and you would jump between these stacks as you returned, which caused some performance problems. So in Go 1.3, we switched to a copying stack where when you ran out of stack space, you would allocate a new one that was like twice as big, and we would copy the stack to the new one and rewrite all the pointers on the stack, but not the integers. So having stack maps that had precise information about what every offset in the stack was meant that we could also use that precise stack information for the garbage collector. So we could have a type precise aware garbage collection on the stack. Go 1.4 basically continued that in Go 1.3, and we had more type awareness everywhere, and the stack sizes went down to 2K. And yeah, so every release basically just gets faster, and garbage collector is getting better and stuff. Go 1.5 is the one that we're currently in stabilization for right now. It has a concurrent GC that promises that there will only ever be a 10 millisecond pause in the worst case. I mean, in general, it's like a 1 millisecond pause. So we also have no C code anymore. All of the compiler and linker have been translated automatically into Go 1.4 code, and then we'll actually be using Go 1.4 to build Go 1.5, or to build the bootstrap compiler. And then the linker and the runtime and everything is now just in Go. So the runtime was rewritten in Go. So the garbage collector is written in Go, and the channels and the scheduler are written in Go. So it's really nice that we don't have to deal with C anymore. The Go routine scheduler has got a lot better, so we're better if we have these hundreds of thousands of Go routines and they're talking to each other. You kind of want to schedule a Go routine to run on a processor it was running on recently for NUMA, cache awareness reasons, so memory isn't being fetched all over the place. So now the number of processors we use by default, we look at the number of processors on your machine and we'll just use them all. If you want to change it, you can, but the new default is we just automatically use them all. In Go 1.6, there's more garbage collector plans. We're going to have HTTP2 on by default. I always like to show this demo of HTTP2 where in HTTP 1.1, your browser has 6 connections to the server open at a time, loading your JavaScript and resources and your CSS and JavaScript. But in HTTP2, it doesn't matter what your latency is. You just request everything at once. So here's like 1 second of latency, and your 180 tiles all come, whereas 1 second of latency, like a satellite internet connection and loading HTTP 1.1 stuff, takes forever. So we'll have HTTP 2.0 on by default for the server and the client. The compiler is getting a new SSA form, and we'll have a lot of better code gen. I don't know. We don't really have all of our 1.6 plans done yet. But we have a few minutes. We do questions, but if you want to learn Go, go to tour.golang.org. It's a little thing that walks you through exercises, and you click next, 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 and there's different little guides, and you could run code over here, and it'll tell you to do things. It's kind of a fun way to learn it. There's also golang.org has a bunch of links to resources, and there's a lot of content online and books online and stuff like that. But that's about it. We can do questions in the few minutes that remain. Yeah, the question is, what architectures does it support? And the answer is that readable? We can make that bigger. We support many things. So we support Android, iOS. We support, Linux or Windows, 32-bit and 64-bit. Linux on ARM, ARM5, ARM7, ARM64, PowerPC 64, Little Endian, and Big Endian. FreeBSD, OpenBSD ARM, NetBSD 3. Oh, we don't have our NetBSD 64-bit builder.
That means that for fun, when I have some free time, I can even in my tablet program something.
Yep. Yeah, there's if you have an Android tablet, there's like a Go playground that's available on the store that you can write code on your tablet and play with it. So yeah, we run on everything, including like Plan 9 and Solaris and native client, and so. And this is only for the main compiler. GCC Go will do like MIPS and IRIX and like weird things. So we run everywhere. Oh, I thought I saw a hand.
There was a promise that Mark's garbage collector house will be no longer 10 minutes. So my question is there a kind of limit in terms of the memory consumed by the application or the allocation rate from this implement?
The question is about the promises from the Go garbage collector about memory. I mean, the memory usage could be like twice as much as what the heap was before. But if
you have 100 gigs, for example, of the heap size, can you still maintain this?
Yep. Yeah, the question are there limitations on the heap size or memory allocation rate? And no. There's a document that explains like how the new garbage collector works. But basically, if it's not able to keep up, then your allocations end up taking part in the garbage collecting and making progress. So it'll slow down your allocations to help out the garbage collector, and then it'll adapt and learn the new the scheduling policy for when the GC kicks in. But
You said that Go is great for tooling. And what about the microservices? Is it good enough to be used as a small service, as a small router or something?
yeah, so the question was Go is good for tooling, but what about like microservices? Yeah, like Go is amazing for microservices. You could write clients and servers really quickly and has like really good introspection for like latency and memory usage and deals with failure as well. So I mean internally at Google we use it for tons of microservices. So
Does it have any support for, let's say, databases right now?
yeah, so the question is, does it have support for databases? There's the Mongo people said of like the best driver for Mongo is the Go one called MGO. So yeah, this is the best Mongo one, and there's Postgres, there's Oracle, there's MySQL. So it basically supports all the databases. But is what? Oh yeah. Oh, so all Go APIs are blocking. There aren't like callback version or async versions because Go routines are built into the language, and Go routines are so cheap. All the APIs are simple and blocking, and you don't have to deal with like, oh, that'll be ready in 2 seconds because I want that callback. You just call a function, and you don't care if it takes 2 or 3 seconds. So anyway, we're about out of time, so you can bug me later, but I encourage you to check it out. It's a really fun programming language that kind of made me like programming again. So, yeah.